few others who are yet to join, but probably they'll be able to join us. Number two, I hope everyone had a restful weekend and you are ready for this class. So a bit of preliminary, we will have a discussion on what we were doing last time. That is the verification, the validation of a model. And after which we'll take a short break. And then from there we'll have another discussion for something slightly different from what we were doing. That is, we'll look at something about questions. So that now having understood what a model, the role a model does in a program, we'll then now move into equations. So having said that, so let's reflect on what we did last time. So generally, last time, to flip through, just for purpose of having everybody on board, we started looking at verification and validation of the model. We gave a distinction between verification and validation. We said verification is focused more on model is right, how you build the model. In other words, are you building the model in the correct way, building? So basically, how you build the model. This is like saying if the model is supposed to have variables, do you have variables? If the model is supposed to have independent and dependent variables, do you have them? So that is basic questions, really transforming. It's a way of saying transforming a problem into a model. So how have you built, the model? How have you built the model? Is it actually in consonance to what the model is expected to have? Model right. Then number two, we said validation is slightly different. It focuses right model. So you may build a model, but is it the right model? The right model is that it is able to perform what is expected of it in terms of its consistency. Because you say a right model should be able to give right answers, consistency. Then we also looked at the various phases in model development and validation or model simulation. We said that there are potentially two distinct sections. That's the run-in and the steady state. And we said that the most critical phase here is the steady state, because in the steady state there isn't new development. In other words, there is no building of the model, but rather you are implementing the model and you are expecting your model to perform that which is expected. This is where you pay more attention. Otherwise, run-in is where there is active development and adjustments may be required. We also talked about validation can occur in various levels, at the abstract stage or abstract level, and it's also at the implementation level. And we actually said what each one of these is. We also looked at what we call the cyclic nature of verification and validation. And in this case, we are looking at basic aspects on one side. We are looking at real system up there, and on the lower side, you are looking at the simulation. You are able to compare the performance of the model vis-a-vis the real scenario. And then in the real scenario, we say there is the cause, and then the cause will lead to an effect. And hence it's something that in research we normally say cause-effect relationship. And in the model or in simulation, we are talking about input and then there's the output. So we can actually therefore relate the cause to be related to input and the effect to be related to output. And in between, we talked about the models, one which you talk about conceptual model that one is going to have and how it relates. We then moved on to now start representing this in a mathematical kind of form. So we said that you can have what we call a base conceptual data model. And in the base conceptual model, we say that this is really an experimental setup. So the experimental setup can actually be seen as that which is at the base conceptual model. And then the next level, we said that the base conceptual model can actually be changed into what we call now the conceptual model, whereby now you've converted this into a conceptual model that we have talked about in the diagram or in the figure above. And we said that essentially one will want the conceptual model to give the same outcome like a real system. That's why we say the conceptual model is equals to the real system, meaning that if this is ideally what somebody expects, that a conceptual model is representing a real system. That's why we are actually talking about in this particular equation, which is more or less like when you are saying if somebody has a blueprint of a house, then we expect now the real house, when it is built, to be a representation of that conceptual model. So this is what is expected at this particular level. Then the next is suppose that here is a supposition that the Amokum are in an experimental frame, meaning where you want, where you are performing an experiment. You are actually saying, suppose you put these two. In other words, there's a model and there's a real system, and then you want to compare the two. When we talk about experimental frame, here is like, I'm sure you know what we call system implementation strategies. One of the experimental implementation strategy is what we call parallel implementation, meaning that in parallel implementation, you are bringing in a new system and the existing system. So you want to compare, as the new system is actually coming in and the old system is there, you want to see their performance in terms of outcome. You want to see which one is doing well. So in that particular case, it's more or less like, so since you are using both of them, we actually say that they are under the same experimental framework. So with that experimental framework, we then are saying that perhaps the performance of the experimental one, or the performance of the conceptual model, the system that you have designed, should be the same as that of the real environment. So that is the aspiration of any model. You do not want to have a model which, when you put it, it gives you different output from the one that you get from a real environment. So mathematically, therefore, we can actually represent this. And you can see really it's a description. Because when somebody buys something, he expects it to perform precisely on how it's expected. That then relates us to what we call, how do you then evaluate? How do you then evaluate your model? If this is, if number 2 is what you expect, then how do you evaluate? We said there are a number of evaluation that you can actually do, and this evaluation is on what we call the validity tests or validation of your model. and we mentioned a number of them. So one of it is replicative validity, which is given here. In replicative validity, we are actually saying you want to produce similar outcomes. That's what it means, similar outcomes, given the same experiment. E here becomes experimental forum. In predictive validity, it means you can actually predictive brings in the ability to predict, meaning that accurately your model can give a prediction using existing data, which is similar to what a real system can give. Meaning you use your model to give an outcome which is similar to that of the the base or the real system. And so we also say that for predictive validity to occur, then there is a presupposition of the first validity that we talked about, duplicative validity. There is also what talk about structural validity. And in structural validity, we are here looking at the movism. In other words, in terms of adaptability. In fact, structural validity is another way in which we talk about systems should be. Remember, one of the characteristics of a good system is adaptability. And adaptability meaning that, therefore, if you change, various input structures, then your model should be able to accept and should be able to take such kind of things. That's why I focus on the structural relation between the real system and the conceptual model, whereby in this case you are looking at ideally the building blocks on the structure in which you are building your model. We also looked at what we call particularly when you are looking at structural validity, we also talk about D simulation, which now D in this particular case, we are looking at even the data aspects that come into it. And we said that in a simulated experiment, a conceptual model, and it does is thus a source of obtainable data denoted by the simulator. So in this case, we are looking at the data which can actually be obtained from there. So we are saying in this particular case, E equals to null, we are saying irrespective of the environment. Yeah, and when you talk about system being adaptable, it means that if there is a change of an environment, it works. Let's reflect on this a little bit seriously. If you look at system, we normally say, I'm sure you will always hear this being asked in projects that you do, that is your system adaptable? Meaning, if I am using a desktop just on the structure, then I can actually be able to see my work precisely. It can actually be able to display the interface very well. If I use a phone, it should be able to fit perfectly in the phone. So that then we say that the layout is adaptable. That is at the structures aspect. One may actually look at it in the sense of now the data that one is going to input in order to, give an outcome. How well does it accept the various data formats that you give it? So, and that therefore it's independent of the environment. I think that's where we stopped last time. So today I want us to look at another section of validation and verification. What we call how do we validate a model in ordinary circumstances also. Whereas what we have discussed there is what we call theoretical. From theory, that's how it's expected. But in practice, in real circumstances, what do we get? So we can validate through what we call existing systems, validating existing systems. How do we validate existing system? Now, this is an important element for us to be able to reflect. If you went somewhere and then there is a system that is put in place, we normally say initially that that system must have been put in place to do something. So the question then is, you ask yourself, does this system give what it was supposed to give? In other words, if I put in a specific input, do I get the expected output? There is what we call expectation. And in that particular case, that's what we normally say a good system, because if you put X and you expect Y, then we are saying you should be able to get Y. That is what ideally a good system is expected to do. So when simulated system exists in real life, then the most obvious and the best approach is to use the real world inputs. This is very important. And this is an aspect that we must pay attention. And here I will give an example of the systems that you are doing for your IS project. If you are saying that you're doing, let's say, farm produce tracking, system, one would then expect that you use real data appertaining to that particular environment where you want to do your study, right? Or if you're saying you're doing maybe stock market analysis, a system for stock market analysis, then one would expect that you would see data relating to stock market. You will not then now again go use data maybe in respect to maybe selling mangoes in a village. The two are slightly different. So ideally, that is what we expect that we'll be able to have. So real world input to the model and compare its output with that of the real world inputs. This is very important. So you are using real, world to compare it with the real world input and output. So that is what we call validating existing system. Using, in other words, the best, and actually we for undergraduate we have not been that too strict, but for masters we are. That if you say that this system is going to use, to assist, people, maybe like this student, I think, who's trying to come up with a system on tackling issues of data management as far as fish farming is concerned, then we will want to expect really what's known, what's really happening, and such kind of things. You cannot pick any other data which is different. So that's what that first bullet is trying to explain. So that's what we call validating existing system. Use real world input and compare it with the real world, output that's expected. There are, however, challenges associated with this approach. Many of them are to do with availability of data, but let's check. Now, the first one is may not always be easy to obtain input and output data. And this is very important. And here, so most of, because here we are saying you need real input. So if you need real input, then it means you must correct it from the source. Now, I can give an example on this one. There's a student I was supervising, and I kept on reminding him that there is a challenge he's going to face as far as data is concerned. But he kept on saying, no, I know where the data is, I can get it, which is within his right. What was the student doing? The student was doing a system on analyzing the investment challenges people go through and their potential implication on the performance of the bank. I want to, like, people deposit the money, all right, in the banks. So, and they withdraw money from the banks. So those characteristics of depositing, withdraw, and such kind of things of various individuals, can you actually, can it be used to tell the bank that you are actually having maybe a potential risky customer? That was the question. Now, from machine learning or data mining methodologies, it's possible. But what do you need to do that study? You need data of the customer, so that you are able to know how this person deposits, how this person withdraws, and such kind of things. So then you are able to analyze that data. Now, that data is held by the bank, but it doesn't belong to the bank. It belongs to the customer. So meaning the student needed to get the consent of the owner of the account, because the bank is under instruction not to release customer data. But now here is a student who says he can actually get that data. Then the next question which comes is, how did you get this data? Who gave you this data? So you see, that brings challenges. So it becomes, so you can't obtain that data, right? So it's, you see, he's doing a legitimate kind of study, and I can tell you it's a good study because I think maybe you may have read most banks in the 90s, 1990s were crossing down or collapsing simply because of customer manipulation of the accounts. Meaning people could actually withdraw and then cause panic withdraw, and with that then it means the bank can't survive, and ultimately a number of banks collapsed, or a number of banks had to merge in order to survive. So it's a legitimate kind of study which can actually be used to predict the likelihood of a bank collapsing. But then data is not there, so may not always be easy to obtain input and output data. That's one challenge of validating existing system. The other thing is, even if you could get actual input output, there's a stroke here, sorry, of an existing model, it will not generally be for every long period, right? So what does this mean? When you like a study like the one example I've given, you see, if somebody deposits today and withdraws tomorrow, that is a single kind of transaction, because here you are saying you want input output. So in this particular case, if that be the case, you can see you can't use that single or two transactions to make an inference. You will need a long period of time. Maybe you want maybe over a period of 1 year for you to make a good analysis. So you will realize that getting data for such long period of time may not be possible, or may not be existing, right? And I can also say this, that if in the circumstance like that particular example, we recognize that transactions, there's a time transactions usually happen, and there's a time that they do not happen. So how then do you manage such kind of disparities? That is also what we call the long run challenges, which leads us now to part 3, that to establish that the model output and the real system output are practically from the same population is not possible also. Okay, so in other words, here, and this is very, very important because up there we talked about frame. And we've said frame is very important because it determines how maybe a system is implemented or an experiment was done. And in this, I can give an example of, you see, if somebody conducts a study this year and another one conducts a study next year in May, you recognize the circumstances may not be the same. For instance, currently we are experiencing COVID challenges. Maybe next year we might not have the COVID challenges. So in that particular circumstances, therefore, they are different. And therefore, the output is likely to be different. To put it in context in the statement there, you recognize when you are doing modeling, you are doing modeling in an assumption, rather within an assumption framework, that the things will be like this. Now, when you go to the real world, you realize that the things are slightly different, right? So that then presents practical challenges. And that's what we are saying, that fine, you assumed these conditions in order to build the model, but what's on the ground is totally different. Okay, so these are some of the issues that are there. And therefore, how do we overcome some of these particular challenges? There is no single strategy, but it is a question of what we call conducting due diligence, meaning you conduct proper analysis on the circumstance under which you are going to perform this your study or this your model. Therefore, the next thing, if the output to be compared as sample means, this is an example to illustrate this concept. When we say sample means, the example is average queue length, waiting time, idle time. So here we are saying if the output is like you want to know, how long are people stay in the queue, what's the average length of this queue, what is the time when somebody is staying idle, there's nothing happening in this particular system. One could use any of the number of statistical tests, what we call goodness of fit, to measure the discrepancy between the output, the two output, that's the model output and the real system. What does this mean now? This is an important element of another way of overcoming these practical challenges that we have talked about. I do not know whether you did hypothesis testing. I do not know. But what we normally say hypothesis testing is that there are a number of methods that have been developed to check on a validity or the trueness of a given statement. You are aware that an hypothesis is a statement that must be tested, and you conduct a test, meaning that you check whether that statement is true by doing statistical tests. Now, some of these statistical tests include what we call the chi-square test. There is another one which we call t-test, f-test, among the many tests that one can actually do. Now, each one of these tests is aimed at assisting one to be able to say your model is good or your model is bad. So when we say goodness or fit tests, you are actually trying to say how well does your model fit in the data. maybe I need to explain this a little bit. If you remember, a scatter plot. A scatter plot is what you are drawing like on a Cartesian plane, you plot points. When you plot those points, then you draw a line which passes through most of these points. The desire always is that you want a line which passes through all the points. But sometimes you'll find that the points are not on a line. And therefore, you may wish to draw a line which is straight, but passing through most of the points. So in that particular case, that line then, you can try to come up with a relationship or an equation that explains it. That formula that explains it, we call it a regression line, as it were. So in that, what you are trying to do in this particular case is what we call goodness or fit test. You want to see whether this data can be fitted into that particular line. Then with that line of fit, you try to see how many points are outside, outside the dotted line. Okay, so I think I will want to use a different slide to be able to explain that a little bit. In a minute, let me plot something for purpose of you being able to see what I'm trying to say. I hope now you're seeing this, right? So what I'm saying, suppose therefore we have just to demonstrate, I have a Cartesian plane. There will be a slight delay in this because of some obvious reasons. With that Cartesian plane, then now what we then have the best line of it. Let's say we have a line like that. Then now assuming up here, let me just put let's say I have X there. Good. So in this particular case then, I hope everybody is able to see this. So what it means is that this is what we call the best line of fit. The best line of fit means it doesn't have to pass through all the points, but it can pass through the middle of this. So in this, therefore, we want to check, and for you to produce this line, you must use an equation. And that equation is what we are calling a regression equation or your model. So then the next thing that I mentioned on the other side is that you want as one of these points to be on this line, but there are those which are, like this, which are outside. So the ones which are outside, like this and this, or perhaps I could change this one, I call it M. I call this one M, and also this one, let me call it Q, for purpose of demonstrating instead of QN, something like that. So it means N and M observations are outside. But there are realization from what we are saying from the real world. Because for you to plot, it means you must have obtained that data. And so that's what you are plotting. So what we need, therefore, to pay attention is the difference. So what happens is that along here, all these points which x, 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 we can obtain their mean. We can obtain their mean. We can add them together and obtain their mean and all such kind of things. But ideally, we also say that if this is therefore becomes the mean, then we want to see the difference. How far is M from the line? How far is N from the line? The desire is always to ensure that the difference between M to the line or N to the line should be small. If the difference between M to the line is small or N to the line is small, then we say you have a good fit. If it's large, then you have a bad fit. And therefore, in that particular case, therefore, what does that mean? This is very important. We normally say that usually the mean is almost known. The mean is always known. In fact, as we are going to talk later, in maybe chapter 3, we call it expectation. Expectation. Okay. Now, mean is also called expectation. Because why do we call mean expectation? Because it is what is known, is what is expected. So, and that's the whole aspect. Whenever one has a system, there is an expectation. That's where I started from. So, you want, therefore, an observation to be as near to the expectation as possible. But if the observation or the outcome of your model is far off from the expectation, then we say your model is bad. So I hope that clarifies this point that I'm explaining here. That is basically what it is. That's why you say to measure the distance between the two outputs. The next thing is that one could also use hypothesis testing to determine if there is any significant difference between, say, the average of the dependent set of observation. So when we are dealing with what we call test of hypothesis, we conduct what we call significance tests. And sometimes you normally say, well, yes, there's a difference, but it's not so significant. Okay? Yes, there's a difference, but it's not significant. And here I will pause and give practical example for purpose of explaining this. You've seen people who conduct, surveys, market surveys, or whatever survey that they conduct. They usually report and actually say that this data is corrected with a kind of how they usually say confidence level. They say we are confident, maybe a confidence level of 95% or a confidence level of 99%. So what that means is that there is some error. There is some error. If somebody says 95%, then it means there's a 5% error. Now, what does that 5% error mean? The 5% error means the significance of it, meaning that, if I must accept the analysis, I must accept that perhaps the 5% does not cause any serious, change, or can't cause any serious change from the truth, right? So that is the statistical interpretation. If someone says 95% confident. It means, therefore, that 5% is not so can't change, the whatever you have from the real truth. So that's what that statement is trying to explain there. The next aspect is so this is the first part when you are dealing with what you call validating existing system. This is really comparing, therefore, the model with the real system in a real environment. There's also what we call validating first time mode. This usually is used on what we call calibration, validating first time mode. In engineering, this is called calibration, right? Like you are actually setting, if for instance it's a machine, to the basic measures within which it's going to operate. And this is commonly used when you are dealing with what we call quality systems. This commonly to test for non-existing real system. That's because there isn't anywhere where you are going to. That's why you are even saying it's for the first time. Remember, when something is first time, so you must set the standards. And I must indicate just before this class, I was discussing with some county representatives on standards. And therefore, you must start somewhere. When you don't have standards, you must set them. There's no reference. So we call it first time mode. And therefore, we call it the calibration. Others will call it zero standard before you move to number 2 or 3. Most of the simulation models are based on assumption, and these assumptions that are tested for validity, because you are saying, I'm assuming this. So since you do not have any other existing to compare, then you test those ones. And therefore, how do you test this one? So there are a number of guidelines that are used in the first time validation. It's what we call subsystem validation. In other words, you are checking on the various. Remember, a system we assume is made of small sections. So can you check the performance of those other sections that form the whole? So a model itself may not have any existing system to compare it with, but it may consist of known subsystems. Each of that validity can be tested separately. A continuation on what I was devising. These are practical examples I'm trying to give. Is people want to do something in their county, and I was trying to tell them, fine, if you want to do this, what's the assumption? They were like, if we are assuming different departments would use this document to do their work. Then I asked them, are you saying they don't have some working rules at the moment? The answer I was given is like, yeah, they have. Then I told them, fine. Now, whatever assumption you are putting now, can you go back and check whether indeed it is in line with how they are doing? Because remember, systems do not actually bring anything new. They only improve on performance, and this is very important. So it is at that point that somebody realized, oh, fine. Therefore, I need to go and actually check on how they're doing, so that whatever I have put here, it does not bring more problems. There is what we call also internal validity that you need to check as a first time. So here, internal validity is reject models if it has high degree of internal variability. So when we talk about internal variability, it means whatever I've given on that chart that I drew, meaning that you do not want a system which now gives results or outputs which are far off from what the real system is. If you have a model and when you use it, or a system when you put it in place and it gives results which nobody else can accept, then that is really, it suffers from internal validity and therefore should not be should not be taken. And this is very, very important in system implementation. Now, a stochastic system with high variance due to its internal process will obscure changes in the output, and therefore the replicating or run would be a problem. And so basically the answer in this is, or the explanation here is, you want a system or a model which builds a system, and that system should be able to give results which are near normal or near expectation. If the variance is too huge, for instance, if M was far off from that particular line, and M is a sort of a model, then that becomes a wrong kind of model that you are having. The other one is what we call sensitivity analysis. This is a very important element of any model, and any person who does a model and tries to say that this model is working is expected to demonstrate sensitivity analysis. And I must indicate here that in what's going in the COVID situation, all drugs and such kind of things are being tested on sensitivity, and including the models that they use. Never mind a few that I saw the other day, people plotting a trend curve, and that is a model. Well, it is a model, but at this very basic, yeah, a trend curve. You use Excel and then you plot and then you say this is a model. Yes, it is, but it's basic. But a good model must be tested on sensitivity. What does that mean? Sensitivity means here, from first understanding, is that does your model, any change, any small, slightest change in input, does it lead to an unseeable kind of output? Or you need to put something huge for you to be able to notice something in your model. So we say sensitivity is that which is able to respond and they give an outcome at the slightest input. So sensitivity consists of systematically varying the values of parameter or the input variables one at a time while keeping all other constants over some range of interest and observing the effect upon the model's response. So you may actually want to reflect this when you are doing your experiments in earlier years of your studies. You could actually put some little chemicals and then try to see, how does this change? Add some, maybe water, and then try to see how the temperature is changing and that kind of things. So in other words, you are not pouring these things as one. You are putting little by little. So, and that's why we are saying your model should be sensitive to any slightest change in respect to whatever that you have put. Then we say it's a very sensitive. That's sensitivity analysis. We tell to which parameter the system is more sensitive, and that is really essential. In medicine, what they do when they are trying to give, to know the kind of drug that somebody should be given, they also look at the dosage, they look at the quantity, they look at a number of other things. So for instance now, and that's why it takes time to get a drug approved. So they want to know, okay, if we are given this quantity, the person you have given this quantity, what are the constants? Constants would be what we call the biomarkers, things like, okay, the weight, the age, the gender, so they need to. So, and you see now, they're not going to give one person a dosage, having considered those parameters, and then say, yeah, it worked on this parameter. That will be not correct. They need to compare it with other, and that's why they take a lot of people, so then they are able to know, okay, if we gave this, he responded this, and the other one with similar characteristics responded this, and the other one with this responded this, then you say it is consistent, which then now goes into the first type of validity, which you talked about, replication or replicative validity. And then now it assists you to get to know which parameters are very important in determining of these things. The other one is face validity. You have always heard on face value and these kind of things. Now, if the model goes against the common sense and logic, it should be rejected, even if it behaves like the real system. That's what face validity means. I mean, there is what we call a normal. So if your model behaves abnormally, out of normal, then it cannot be, even if it, you know, it is you know, there has to be some common sense in every logic. Yeah, common sense. What do we expect? Even if the whatever you have actually given there is from the real environment. That's what we call the face value. So basically, that is what validity and verification is all about. So in summary, we are saying, what were we doing here? We needed to understand what's verification. How do we verify? We are saying, am I having ability to build a right model? Have I built the right model? You know, that is model right. Have I built the model right? Then validity is the model right? Building model right, and then the other one is right model. So have I picked the right model? Have I looked at the circumstances and it is the correct one? So with that, then we've checked through most of the aspects that are very critical, which you can easily apply in your circumstances of ISS, rather IS project. So I want us to take a break of 30 minutes. You may log off just to break if you can, or you maintain. So we'll take a break of 30 minutes, but there is something I want you to, as an individual, to be reflecting. I don't want you to be doing anything on the machine now, but I want you to reflect on something. An environment where you can give an advice. In an environment where you can give an advice on how they can validate any system they may want to bring on board. Remember, there are various environments, even where you were out for your industrial attachment. And remember, we said, you know, systems are everywhere. So reflect and consider an advice that you can give to those people if they brought in a new system or a new model. What validation can they do to that particular system? Remember, validation is really is like telling somebody, now the reasons why I want you to buy this system is because of A, B, C, D. So now I want you to reflect on what advice you can give those you know, people who are going to procure that particular system. How do they validate that which they need based on what we have discussed? So I will, when we come back, I'll be asking in a random manner any one of you the question to respond to that. But before then, there's a question on the chat. Could you please explain the first challenge when validating existing, the part that says without distributing? The first part is where we talked about existentiality of data. That this is it. Where we said, and as I said, that sometimes it's very difficult to get the data that can actually be able to validate what you've actually done. I gave an example of a student I'm supervising at masters, and he has a very beautiful, problem to research on. But then the question was, who gives him that data? Because the data belongs to somebody. So if you are actually trying to say that this can actually be done, then can you get this data? Can people give you this data? If they cannot, is there a data set somewhere which you can actually get to be able to validate your model to show that it's working? Now, from real system without distributing it, that's what it is like. If somebody gives you this data, you are given in confidence. If somebody gives you, that's why I say the bank is the custodian of this data, but they are not the owner. They are only the custodian of the data of the customers, but the real owner is the customer. So even therefore, the customer, rather the bank, cannot distribute it. Number one. Number two, the researcher cannot distribute it. That's number two. So then it becomes very difficult for you to be able to demonstrate out there. That's what it means. Good. Any further clarification before we take that break? But please remember, it's a reflection point. You reflect. I'll ask any one of you that question. And I'm going to put that question on the chat. If you may want to make reference to it, you're most welcome. But we will resume at 12:50. Great. Take 20 minutes to take presentations from a number of you. So I'm going to call you to share with us your thoughts. So, and I'm going to start with Ngugi John. Ngugi John, please share with us your thoughts.
Hello.
Ngugi John, I can't hear you, please.
Hello.
Yes, maybe speak a bit loud. Ngugi, are you around?
Hello.
Yes.
Okay. So if the organization wants to implement a new model,
Yes.
so okay, first, first I think they should identify which model they would like to adopt, and then after that, okay. So for my case, I was thinking of face validity.
Yes.
So, hello.
Yes. Yes.
So, okay, in the case of face validity, so I think what they should do, like if they have existing data, for example, they should, okay, then they should take that data then as their input and then pass it through the model, then compare their output with the output from the model with what they already have. If it matches up, if then they looks wrong the model and so on.
Um, Which organization, you could give us an example?
Okay, let's say,
Maybe as you
for
reflect on
example,
that, as you reflect on that, I can take another one, but I'll come back. Is that okay?
yeah.
Oh, great. So the next is Mbali. Mbali, I unmute you. Please go ahead.
Okay, so for considering the validity in every is a very key of the successful implementation. I was basically looking at the AI field, whereby we are looking at the validity, we are checking if the model that we have created match the outcome of a specific organization. So I was looking at basically AI in medical fields, whereby we are trying to do like classification. After giving our model a specific set of data, we try to look if the model can relate to unknown data and be able to predict. So for me, it was basically face validity and sensitivity analysis, whereby for the sensitivity analysis, it should be able to look at the change on a specific image and be able to predict at slight time. So that is what I was thinking about.
Okay. Thank you, Mumbari. Maybe on face value, how will it work?
For the face validity, can I look at it first of all before replying?
Okay, no problem. Actually, I've also put I think I've shared the slide on face validity, which we say the model against the common sense and logic. Eh? Yeah. I'll hope you won't mind if I came back after a minute.
Okay.
Great. So the next presentation will be Anita Kivindio. Unmute you, please go ahead, Anita. Anita.
Sorry.
Yeah, sorry.
Nasikia natajwa hapa kwa hii meeting.
Okay. So you how
One
did
minute. Yes.
your question, how did you respond to it?
Nini ni shati?
Anita, are we together?
Ati?
I assume Anita is not with us. So yes, Gabriel. Gabriel Mbogwa. Gabriel, can you hear me? Mbogwa.
Oh,
Yes, how are you?
you hear me?
Yes. Yeah, your hand is up. You can go ahead.
Please ask the question again.
Your hand is up. Perhaps you wanted to ask something.
Oh, no. It was a mistake.
Oh, sorry. So Anita, when you are ready, you let me know. I'm waiting. So next is Esther Njoroge. Esther, and you can go ahead. Esther Njoroge. Esther. Do I assume Esther is absent? Esther, can you speak loud? We can't hear you. I take it that Esther is not present. Because when you get back, you let me know. Otherwise, I'll be marking you absent. Then I pick Miriam Mboga.
Yeah.
Maboga, sorry. William,
So for me,
yes.
I chose the e-commerce model
Mhm,
based on an example of Jumia and AliExpress.
mhm,
So the model is suggestion of products. In this, space validity goes on common sense. So if I am trying to advise on a suggestion of products, face validity works because the basis of e-commerce is availability of products and their prices. And then on subsystem validity, in
mhm,
this, we compare the existing model to
mhm,
something that is either being used by the organization or not. So, the suggestion of products to a user or a buyer, I've compared that to YouTube algorithms, whereby as a user goes to check on videos, they are whatever they view uh, comes influences what YouTube suggests for them to view later. Like it says, those others who watched this video also watched this person. So in the e-commerce system, the model for suggesting products, if someone views foodstuffs, they could be suggested to check on kitchen appliances or cutlery, and that is subsystem validity. And then sensitivity analysis, this checks on parameter sensitivity and building confidence. So in this, the parameters for suggesting the products could be categories. So uh, categories as a parameter will be sensitive to the model, since the model can only suggest products to a buyer based on given categories. As I said, the category of foodstuffs or kitchen appliances or maybe clothes, such. But then a parameter like location could be a bit insensitive, because if you consider that, if you'll have to consider aspects of like where the request or the user is viewing the products from, which could in turn be like a bit invasive. So I would think that location will be an insensitive parameter in that. So I've based on the three aspects. Yeah.
Okay. Thank you, Miriam. Good analysis. Good analysis. Maybe I can give out a rejoinder
Yes.
on sensitivity is not about privacy.
Mm-hmm.
It's on model is more about how reactive does the model become considering a change of a parameter. In other words, is if a slight change, can it actually be registered? Say that there are some systems when if you put a small amount of input, it doesn't show until you put a lot. So if you reflect it on that basis, that will be good. But on the other side, yes, you could actually look at sensitivity in respect to that confidential or what we call private data. How how does it handle it so that then it is able not to be too invasive, all right? So then it's able to respond and maybe not to reveal too much, but at the same time use that data in a manner that is consistent with data privacy. Good. Thank you for that. There was a hand up by Anton. Yes, Anton.
Oh, so for what I was thinking,
Yes.
I was thinking of a voting system.
Mhm.
So if somebody was to come up with a voting system,
Mhm.
one of the things they would need to take into account, like in terms of the replicative validity, is that that system accurate. At the end of the day, what you want to do is capture the capture what the majority chooses, the person from the um, majority of the population chooses.
Mhm.
So that should be replicated even in the system that you're trying to build or model. So, and in terms of face validity, I was thinking, like, if your model or if your system does something like this, maybe it displays, like, as you vote, it displays like who's winning and something like that. Like, your model would be working correctly, but it wouldn't make sense to give the people like who like the candidates that are winning immediately they vote and something like that. I think it would affect how people vote and all that. And another thing that I think this is could be captured in structural validity, is that the model should capture that each and every person has only one vote. So you can't, like, it can't be a situation where one person has two more votes, and also capture the aspect of spoiled votes, that they shouldn't be used for any other, like, they shouldn't be included in the system because in the real world they are not used. So yeah, that's what I was thinking about.
Thanks, Anton. Good analysis. I really wish that, this could actually be put. In fact, you see, like face validity, common sense. You know what has been happening in the recent past in our country. So good analysis and a good account on how this, and I've liked on the structural validity how you brought it. That's very good. And in fact, if you look at the way you have put it, it informs therefore on what we call system logic, on system rules really. I like that. Thank you. Mambali, there was something you were to clarify.
Yeah, I was trying to clarify more on the face validity.
Yes.
I'm not sure about the analysis that I did, but the idea
Yeah.
behind the face validity for an AI for skin disease classification would
Yes.
be like, if we are trying to predict the skin disease, the model should not predict anything right apart from the skin disease. So for the face validity, it would be something like, if you are trying to predict the measles, you should not predict something else like cancer. So the model should be rejected in that case.
Yes, that is correct. Now I like that. I thought you had something very good, and I wanted to be sure that your logic up to the end was clear with me. Thank you. That's very good, and that's actually what's expected. Somebody can actually say, I'm doing this, and yeah, in common sense, it shouldn't be that way, but then in real, it's doing what it is doing. But I like that. Thank you. Yes, Anita, mic is not okay. Sorry, I wish we could hear your presentation, but I hope in future we should. I'm still waiting for Esther Njoroge to confirm whether she got my question. Any question before I introduce something? But generally, I think from those that have sampled, I'm happy with the logic, and I want to believe that every one of us who's here, at least
Hello,
you
sir.
have something. Yes, Njoroge.
Yes, hi. I was away for a while. Sorry that I'm late. Could you just give me 5 minutes to set up a bit? Just 5 minutes.
Yes, please do. Otherwise, I'm having a problem.
Yeah, just 5 minutes.
Okay, fine. So yes, I was saying generally, considering the sample I've taken, I believe a number of us, all of us have gotten these things right. Unless there's any clarification from your side, I will then introduce something slightly, which this one I'm going to take like 20 minutes before we could actually take another break, and potentially we can actually break for the day, because I think our objectives could have been met. So having said that, now I want to quickly take you to our new topic, that is lecture, substantially what I call lecture 5. And lecture 5 is going to be on topic number 3. This is what we call differential equations. Differential equations. In these differential equations, I want to say now I want to give a context under which we are moving into this, and how this topic is going to be relevant into what we are doing. Differential equations is sometimes also referred to as what we call ordinary differential equations. So substantially, you may find people saying differential equations, others calling ordinary differential equations. They are actually used interchangeably sometimes. The importance of differential equations in modeling is that we recognize most in situations that we encounter in ordinary life, they are dependent on a change. They are dependent on a change. Now, and that change, we need to find a way in which we can quantify it, or a way in which we can measure it. And hence, therefore, differential equations provides us a mean in which we can actually be able to establish this change. That's number one. And number two, we also recognize that equations are the simplest ways in which we represent scenarios, we represent circumstances that we encounter in a system. And therefore, we need therefore to find a way in which we can analyze these equations. And these ways in which you can analyze these equations is through this differential equation analysis, or solving the differential equations. Now, to solve these differential equations means we need to find a solution. So, 3 things that are important. Equation is very important. Number one, that we recognize that come and they involve a change. That's number one. But two, we recognize that this change needs to be determined. That means we need to solve an equation. So we know there's a change, there's an equation, and so we need to solve this equation so that then we can be able to quantify that change. That is the understanding. Now, this topic, we are doing it on the backdrop that you substantially can be able to write an equation now of any situation. And in this particular one, I want us to be able to write what we can say a linear equation. Just reflect on a linear equation. And when we talk about a linear equation, it means we are talking about the dependent variable and the independent variable, which are changing in a particular, straight manner. That are changing one influences the other in either a positive or a negative way, but in a linear manner. So we are doing this topic knowing that at least you can actually write an equation and you can write a linear equation. Then the other thing is that we are doing this topic with understanding that you can differentiate an equation. You can differentiate an equation. And you can also find the antiderivative of the equation, or what we commonly refer to as integrate an equation. So 3 things also that we are doing this topic knowing that you can be able to write a linear equation, at least a linear equation. Later on we are going to deal with nonlinear equations, no problem. Then the next is that you can differentiate an equation. Then number 3, you can integrate the equation. So by the end of this topic, why are we doing this topic? Therefore, we are doing this topic because we want to understand the different differential equations and then see how we can apply them in modeling. That we know different equations, then we apply them in modeling. So by the end of this lecture, which substantially we redo it up to next lecture, is that we identify an ordinary differential equation. This is a chart. Okay, let me check. Yes, Njoroge. Now you can present, please.
Yes. Okay. Sorry for the interruption, but so my simulation model was a theme park ride where we look at roller coasters. So we simulate how roller coasters work. So for validating the existing system, the real input will be the number of people that are supposed to be on the roller coasters and the weight, because those two really affect how it really works now, the machine itself. So the replicative validity, the machine itself is supposed to, rotate according to the weights programmed with if the weight of the total number of people is correct and also the number of people. So for predictive validity, in case there is a problem, the model is supposed to simulate that the machine should stop, for faults, in case of a fault detection. And then for the sensitivity validity, in case there's excess weight when people are yet to board the machine, the simulated model should also indicate that, and the model shouldn't really move in case there is excess weight. Yeah,
Okay.
yes, that's what
Um,
I'm thinking of it.
yeah, maybe I could give a comment on your case. Thank you for sharing your case. What I wanted was like you reflect on you know, a system that you know, and then try to see which validity they could actually initiate in case you know, they want to maybe to adopt that another system or a new system or continue using that one. Huh? So that's what I wanted to reflect. But nonetheless, there is a section that I want to assist you on this constructive validity, where you the replicative validity this is like, can you use this roller coaster in another place and then it gives the same, you know, experience and such kind of things. That's what perhaps you could look at. But on the other aspect about weight and number of people and such kind of things, that is more on a constructive, you know, validity, because it is how do you construct, how many, you know, people should it take, what weight should it take. That becomes more constructive, you know, for validity, right? So perhaps I know you came in a little bit fast. You would have more time to reflect on this, but nonetheless, thank you for your presentation. Right. So so we can continue then. So by the end of this lecture on ordinary differential equation, we want to be able to identify an ordinary differential equation. In other words, can you be able to say this is an ordinary differential equation? What are the things that you look at, and then you say this is an ordinary differential equation and not any other equation? We also need to look at the different forms of ordinary differential equations, and perhaps then you get to see how they are used. We'll then solve the ordinary differential equation, which will be the last thing. But more importantly is to understand on how we can use the ordinary differential equation to model a real problem. So all these things that we've been talking about, we want to maybe pick one or two and try to see how do we model them. How do we use ordinary differential equation to represent them? So all these things that we have been learning, discussing different scenarios, we'll try to pick a few of them, then see how we can actually present them using the ODE. So let's then start. This one I will be, I won't be too fast. Today I will type some of the equations. You'll see me typing, but in subsequent lectures, you will see me writing. You will see me writing, and therefore it will be easier. I do not want to put the video because it takes much of your bundles, but I will be able to type using another technology which you'll be able to see next week. But for today, I'll be able to type here and you'll be able to follow with what I will be doing, because now we'll be really doing equations. So we want to ask ourselves, what's this ordinary differential equation? So the ordinary differential equation consists of two parts. It has ordinary derivative. Sorry, it has ordinary derivative, and then it has an unknown function. Okay, so ordinary derivative and an unknown function. Now, when we talk about ordinary derivative, it means it has the differential parts. Remember, differential is denoted by, so differential, derivative. So I need now here to say derivative can be denoted by, I think you know some of this. I hope you are seeing what I'm typing, so that you follow. Noted by a number of ways in which we denote this. The first way we can denote it this way. Let's say I have X and then something up there like that. Okay, so you may find something like that. So that can be a way of denoting, or it can be denoted by, which is what you are, I think, mostly familiar with. I not know. You can say D, for instance, dx for this particular case, or over again d maybe dt. So meaning that we are differentiating with respect to t. So that is a derivative. Okay. A known function can be denoted by a known function, so that now we know where we are heading to. Function, sorry, a known function can be denoted by a function. Ordinarily, we normally say it is f, which stands for function. So we can say f, and inside maybe we say it's a function of x. But because if I'm dealing with the upper one here, you see I'm saying there is x and then there is t. So I'm actually saying dependent on this. So what that means, it means this. How do we read this? We say there is a function of x which is time dependent, meaning x changes as time changes, or may not change as time changes. Okay, you see, if it doesn't change, it means it's a constant, isn't it? And if it changes as time changes, then we say it's a variable. So these two things are the things that you will actually be looking at. You want to look at and actually say whether you are having whether you are having an ODE. So they must exist in a same equation. So the next thing is having defined those, consider the following example of an ODE, ordinary differential equation. So I want to give an example here. Using any one of these scenario, we can pick an example here. Let me use the second part. I can say there's dx. Before I say dx, I can say a. Then now, minute. I can say a, and then dx over dt plus, let's say something like, let's say b of x plus c is equals to 0. Okay, so this is an example of an ordinary differential equation. Why is it that it is an ODE? It's because of the following. Number one, we are having this derivative part. This is an ODE because we are having this derivative part. And of course, we are having an unknown function. We have x that we don't know its value. X is unknown. Okay, x is unknown. I can actually represent this, and you may find this so I'm trying to give all possible ways in which you may find these things written, so that then when you find them written, you are familiar with them. It's possible. I can use the second part of representation. So now we have x raised to we have that x raised to that. So in this particular case, this is also either way. So there's the derivative part, and then there's the unknown. So that is an example of an ODE. It's possible we can have an ODE of this nature. You know, we can have an ODE of this particular nature. And this one I would put something here. Sorry. Then x. So something like that. And maybe this one I can take it away so that then we are not only dealing with one side. I can go on the other side. I can have something like x squared. Right? So this is also an ODE because there is a derivative, only that the derivative is 2 here. Here the derivative is 1, you know, and there is the unknown. So this is how we represent an ODE, examples of ODE. Now, the next thing is how, maybe an hypothetical, how do we solve the ODE? Okay. Like, how do I solve any one of this? Here the answer is we solve them using by obtaining the antiderivative. That is you find the antiderivatives. Okay, so that is how you solve them. So I want us to reflect on this. Okay, so I want to give an example, e.g. Solve the following ODE. Okay, so here is hypothetical for now, but we'll do a number of examples. Let me pick this one here. And I'll make it easier so that then we start small first. Allow me to remove these two parts, but we'll be coming into the complex aspect. This is an ODE. So now we want to solve this. To solve, therefore, this means we want to obtain the values here in other words, here is like the solution is to obtain the values of x that satisfy the equation. That is the thing. So you remember a number of ways in which you could do this. I will mention. So we obtain the antiderivative of the equation. That is the thing. That is, so to obtain it, then it means we need to make x the subject of the formula. That's the first thing. So to do that, we make x the subject of the formula, which means therefore if we take p on the other side, this p on the other side, it becomes negative. All right. So and then it becomes negative b, right? So from there, we can then divide by, this looks simple, and it should be really. And I say I always start from the basic logic. So so the next is divided by a. So then now means we've gotten x, but now still x has the derivative in it. So therefore the next point is to remove. Now here integrate integrate both sides. That is the next point. Say that if you integrate here, then it means the antiderivative goes. I do not need to start going to the first principles. But if you integrate both sides, then on one side, what happens is that then the derivative goes, because we are finding the opposite of it. So what will happen is that on this side, if we obtain the derivative here, which is what I'm going to show, we'll obtain the derivative of this, which is that. Sorry, there's something I need to remove there. That, and also on this other side, you also find the derivative on this other side, right? So with this, but now since we are finding the derivative, we must say with respect to with what here, we assume that x was changing with respect to time, so we'll also put dt there. So with that, once you do this, then the next, that is really basically the thing. So now the next point is once you do that, we on this side, since you have taken the derivative, then on this side it remains to be x, and then this becomes now the solution, right? So this becomes now the solution. Never mind about the limits, we will talk about them as we move. But that's the point. So I need to go back. I believe everyone has seen. So we are saying that so once we have this, then the next point is that we want to solve them. How do we solve them? We have to find the antiderivative, and the antiderivative, I've said it is what we call it integration. I think that's what most of you are familiar with. So an example, solve the following ordinary differential equation. So here we are saying really the whole thing to solve is to obtain the values that satisfy the equation given. And to do that, we need to make x, the subject of the formula, Or, you take, like terms on one side, and that's basically, manipulation. And then it give us what we have actually been able to. So essentially, we are saying that this is now the solution, that if you integrated this, whatever you obtain becomes the solution to the differential equation. Okay. Then the next thing is, unless it's a question up to where I've reached, I'm dealing with the basics, so that when we move to the other levels, then we are all together. Any question? If there isn't, then the next thing we want to do is classification of ODEs. Okay. In other words, do we have any classification? There are a number of classifications, but what we want to deal with here, this classification, sometimes I call it of order. Order of ODE. Okay. Now, how do we achieve this? We first of all, before I even go to how do we achieve the order, on the first case we say ODE or ODEs have a single variable, single independent variable. Like what you have actually seen there, up there, the assumption is that X is the only one. Let me go back. I demonstrate this. You see, in this equation like this, we are having X. So it's very possible there are sections where here we may have Y. Right? That becomes not an ODE. So in this ODE, we are actually saying there is a single, variable, which is independent. That's very important. So an ODE has that. Then the next thing is what we can talk about the order. Now, the order is dependent on the highest power. The order of the ODE is dependent on the highest, I will demonstrate, highest derivative of the independent variable. Independent variable. Okay. So we can actually see EG, so that then we are able to see this example. If I pick, let's say, let's again write another equation here. Let's say we have an equation. Let's say here is X. Okay, and then plus something. Let's say plus AX is equals to 0. And let me again give another one, so that then when we start analyzing, we analyze them jointly. It becomes easier. Let's say I have this, and then here maybe I say P of X is equals to something like that. So let's check on these two examples. So these are two equations which we can check. Now, if you check on this one, we have said that the order is dependent on the highest derivative of independent variable. What's the independent variable? X. X is the only variable we have. Now A, in that particular case, we assume A and B are constants, right? So I think I should have mentioned that. A and B are constants. So the only variable here is X. So when you go here, the derivative is 1, and here the derivative is 2. So now, since this, now there is an assumption here which we have not written. This one does not have a derivative. So please do not therefore actually say that, but that is 1. No. It doesn't, because we have not put this sign here. So there is only one derivative that we are having. I hope this size of this is visible. But if it's not visible, I can enlarge that. So we have only one of this, but this one here is not a derivative. So there's one derivative here and there's a derivative on this other equation. So the highest derivative here is 1. And since the highest derivative is 1, then this one we say is first order. Order ODE. Right? So since here it's 1, then this becomes a first order ODE. Then it therefore applies using the same reasoning. It therefore means that the next one will be second order. Sorry. So the next one will be second order ODE. Equally, we can therefore have even a fifth order. That becomes now a third order ODE. So what therefore determines the order is the highest derivative in that equation. Meaning therefore, how do we solve them? What I've demonstrated up there is for a first order. How do we deal with the second order and third order, or even higher orders? We'll be able to tackle that in the subsequent discussions. Any question? If there isn't, then I can talk about something here. The order of the differential equation is the order of the highest derivative of the unknown function involved in the equation, which is what I've actually indicated there. Then here is what up there I defined. Another way of explaining the things that I explained up here, where we started from here, whereby I said that an ODE can be denoted by this and a unknown function can be denoted by this. So what's the relationship? So you recognize we can take the function on one side and then the derivative on one side, and that is another way of writing. Like now, when you look at dy over dt is equals to this, I want you to reflect on this section here. Sorry. When we reached here, that when we met that to be the subject, it is the same here, except that, so I want you now in this particular case, we can actually say this section is the dy dt. And then this section is what we are calling function of yt, right? So this is this in another way of presentation. Then there is what we call in here note. A function of this nature would have what we call initial functions, rather initial values. Initial values, because remember we said that in this OD there is a presupposition of change. Change from where is very important. So change we start talking about from the initial stage. But I think I'll be able to explain this in our subsequent classes, because if I introduce it, I might not be able to finish it before the time is over. I pause there to take any question or any clarification before we call it a day. You can see the notes here. I'm writing. This now would it slightly change. Some of the notes will be writing in the class as we are doing like this, and then I update it. So I'll update once I clean out some of the things that I've typed here to format it correctly, so that then you can also be able to see it on the e-learning. But this is how we'll be doing it. I'll be typing the equations. I'll be writing some of the equations, and you'll be seeing using a whiteboard, so that then you are able to follow. So do not expect it's right, which are static. No, we'll be writing this together so that you are able to follow. Yeah, where do we encounter modeling? Yeah, you are going to see them basically. I said what we have been doing is we have been describing. Remember, we said that modeling, there is a mathematical representation. So in my preamble today, I've said that we'll be using ordinary differential equations to represent those scenarios, those systems. So once we present those scenarios, we move from the descriptive into the mathematical representation. Now, once we have those mathematical representation, then we try to solve them. That's where we will be using it. So we'll encounter it in modeling substantially. I hope that clarifies your question, the person who asked it. Any further clarification? If there isn't, then I want you to take a break, and then later on the course of the day, you check on how to conduct differentiation. Remind yourself the concepts of differentiation and integration, whereas here I'm supposed to assume you know, but that is not how it's going to be. I think the person asking example of phase validity, I thought from the example given by your colleague, it should be clear. Yeah, I thought there were a number of examples, and because I saw your question previously, and so I thought the example given by your colleagues is sufficient. But if you want one from my side, that's okay, fine. I'll again say that here we are saying that there is you want a system, or you want a model to comply with logic and common sense. Now, if you go to your first course in programming, you talked about errors. And one of the category of errors you talked about was logical errors. If you may remember, that is under Introduction to Programming. One of the categories of errors you talked about is logical error. And now, logical error, what did it mean? It meant that your system will work, but whatever you are getting from that, system does not make sense. I believe that's how it was explained. Meaning, therefore, the system is working. And that's how that statement that I have written on the slide that I shared. The system is working. Yeah. In real life, the system is working, but it's not giving what is common sense. Moreover, Mwambari gave a perfect scenario also in real world. He also talked about here you come up with a system which is going to use intelligence to be able to predict, maybe a potential disease somebody is hailing from. The thing is, yes, the system that you come up is actually giving an outcome, but that outcome is not consistent with reality, and this is what we call false positives. You may remember your AI. I hope you dealt with how to, in artificial intelligence or introduction to artificial intelligence, you came across what we call false positives and false negatives. So meaning that really, yes, it is giving an outcome, but the outcome is out of reality. I mean, it's an outcome, yes, but it's out of reality, or it does not conform to common sense. So if you reflect on that, that's why I have had to go back to your first unit. I think you may have done a while ago, first year, when you're looking at programming errors, and then build onto this particular case. That's how you reflect on it. I hope that now clarifies your concern. The one who asked, are we clear? Or, good. Any further clarification? Now, I want just to do something. I want to put you into group. You will use the 15 minutes remaining to discuss on the ordinary differential equation up to where we have reached. And I will be around just reflecting on what we have learned about the OD up to where we have actually reached. Just basically. And then the one who asked where we can apply this ordinary differential equation, just reflect on this example of, energy equation. If you may remember, all of you, energy equation, or anything which has a rate of change. Anything with a rate of change, reflect on it, and then we'll be able to do that. So the breakout is just reflecting on what we have discussed, no question, just in case your colleague can offer complementary explanation. So I am forming those breakouts now. Please join your breakout. So the rooms are open. Please join your group and share your thoughts, your understanding about the basic concepts that I've discussed today.